All right. So welcome everyone to a new edition of our weekly IC research seminars. Today we have David Paneque from the Max Planck Institute for Physics, and I would like to invite Monica to give a proper introduction of our speaker.
Okay, so good morning or good afternoon, everyone, in my side. So it's a great pleasure to have David Paneque today with us. He's visiting the ISC for the very first time, and it's a pleasure for the Astroparticle Physics Group to have him with us. So David started his career in IFAE in Barcelona as a particle physicist, working in the Aleph experiment in LEP, but then was more drawn into gamma ray physics. So he decided to move to Max Planck Institute in Munich to do his thesis in 2004, working in the MAGIC experiment. Later on, he moved to Stanford for 5 years, where he was working in the Fermi-LAT collaboration. So it's also a gamma ray experiment, but this time in space. And later, he went back to Max Planck in Munich, where he's staff ever since. And he's happily working there. And he's currently the spokesperson of the MAGIC collaboration. So he's a very knowledgeable person, especially in extragalactic physics.
Okay, thank you very much, Monica. And thanks for the opportunity to tell you a little bit about gamma rays. My plan is actually to tell you about how we can use gamma rays to study the high energy universe, to study the most extreme cosmic particle accelerators. And the plan is to tell you a little bit about the merits of gamma ray astronomy, to tell you about the different strategies that we can use to measure gamma rays. And then I'll shift a little bit the focus towards one specific gamma ray instrument, which is MAGIC, where I'm spending now most of my time. I'll tell you a little bit about MAGIC, some scientific results obtained recently, and then I will give you an outlook. So some of the slides are quite introductory about gamma rays. I see there's quite some people now who are experts in gamma rays. There's some part that is a bit introductory. There's another part that is more focused on results. So hopefully everybody gets something from this talk. Good. So I would like to start with the fact that in the 50s, or until the 50s and 60s, basically particle physicists were the same as cosmic ray physicists. People were using cosmic rays to learn many interesting things about fundamentals of nature. In particular, the positron, the muon, and the charged pions were actually discovered with cosmic rays. So back in the day, it was actually quite normal for physicists to bring their detectors to the top of the mountain and try to learn about the laws of physics with the mountain top experiments. After the 60s, then we learned how to make particle accelerators in the lab. And then people shifted their focus towards collider physics, because it's a bit easier to have a control environment and to learn about the laws of fundamental physics, particle physics. But nevertheless, the research area of cosmic rays had evolved, and also the instruments have evolved, and now they became far more complex, more expensive, and require many more people to build them and to operate them. And here you have some photos from some table or mountaintop experiments. Many of you know MAGIC, Fermi, and LST1. Okay, so photons have been used to study astronomical objects for many centuries, but gamma rays are actually it's only since few tens of years that we can use them to perform gamma ray, to perform astronomy. Basically from space in the 80s, 90s with IGRET, there was a big push, and from the ground, the big push happened with the current generation of Cherenkov telescopes, MAGIC, S, and Veritas. So it's a very relatively novel discipline. And so gamma rays are actually a very nice tool to study the non-thermal universe, the high energy universe, because regardless whether the high energy particles have an hadronic or leptonic origin, eventually they will produce gamma rays. And gamma rays tell us about three important information. They tell us about the location of these sources, because gamma rays, differently from cosmic rays, they don't get deflected in the magnetic field. So they really point directly towards the sources. They tell us about the lower limit to the energy of these high energy particles because they are secondary particles, and they also bring time information. They tell us about the dynamics of these high energy particles, and therefore they are really wonderful tools to study extreme environments like explosions of stars, accretion of matter into supermassive black hole, or these extreme electromagnetic fields in the nearby of pulsars. And there are three ways of detecting gamma rays. The first one is directly through Compton scattering or pair production. In that case, you need to bring your detector outside the atmosphere. It only works with balloon experiments of very high up or satellite experiments. And here an example is the Fermilab instrument, which is basically a particle physics detector, the typical detector that one puts in collider physics, where you have a tracker, tungsten and silicon strips, where the gamma rays get converted into electron positron. Then you trace the trajectory of these electron positors, and they tell you from where the gamma ray is coming from. Then you have a calorimeter where the electron and the positron, they lose their energy. And they basically, they tell us, this instrument tell us about the energy of the incoming gamma ray. And then you have anti-coincidence detector, plastic scintillators and PMTs, which tell us when there's a charge, a particle going through. And this is used to veto the event, basically to separate gammas and cosmic rays. So Fermi consists of a 2 × 2 square meter detector with a 1 meter height. It's a 3 tons, 1 million channels, and it only consumes 650 watts. So this is basically 11 light bulbs from the old times before LEDs became fashion. So the lab operates in this energy range from a few tens of MeV to a few hundreds of GeV. And basically it operates, it surveys the entire sky. At any time it observes 20% of the sky, and basically every 2 orbits, one can see the entire sky. So it's a wonderful instrument to see what's going on in the GeV sky. And since there's no consumables, the idea is to keep it operating as soon as possible. If nothing breaks, it can operate easily 15 more years. Yeah. The second way of detecting gamma rays is through the Cherenkov light that the charged particles that are produced when the gamma ray comes into the atmosphere. They produce Cherenkov light, and then the idea is to detect this with telescopes. So basically, you have an incoming gamma ray, you have an atmospheric shower, lots of electrons and positrons. They travel faster than the speed of light in the atmosphere, and they produce Cherenkov light, and they make a pool of light on the ground. And then if you put your detector there, you collect light, and then you measure it in a camera, and you basically make a photo of this atmospheric shower. And then through the shape of this shower and also some temporal information, you can reconstruct the incoming direction of the gamma ray, the energy, and you can separate gammas and background. And if instead of one telescope, you have several telescopes, then you have a stereo image, and then the ability to reconstruct the incoming gamma rays is much better. And the third way of detecting gamma rays is through the direct detection of the particles in the shower in a extensive shower array. So basically, these are detectors that are put very high up in the atmosphere, and they detect the tail of the particles in the atmospheric shower. An example is HAWK here in Puebla, in Mexico, where you have 300 tanks, and then when the particles go through these tanks, they illuminate these PMTs, and through the number of hits and the distribution of hits, that they can separate signal and background, and they can reconstruct the incoming direction of the gamma ray and the energy of the gamma ray. So that's basically how it works. And the interesting thing is that all these different strategies are very highly complementary. Complementary in terms of the energy range, as you can see here, from tens of MeV up to PeV, a few PeV. Then we have the duty cycle. In this case, duty cycles are very high. They basically operate almost all the time. While in the case of Cherenkov telescopes, they can only operate during good weather, night, no moon. So duty cycle is at the level of 10%. Fields of view, these are very large fields of view. Cherenkov telescopes have small fields of view. And then in terms of sensitivity, Cherenkov telescopes offer the best sensitivity. So that's particularly important if you want to see flux variations in the sources that you want to study in short time scale. Then the best instrument is by far Cherenkov telescopes. But these guys, because of the field of view, are also very good to catch transients, because you don't know where the transients are, so they can tell us when something flares in the sky. And yes, so in red, you have the generation of instruments that are operating, and now the new generation of camera instruments is now coming online. In the case of LST, ASTRI, and LASO, also producing lots of very interesting results. So now we have the previous generation of instruments, the new generation now overlapping. I think it's important to stress that in the last 2 decades, there have been a spectacular advance in our knowledge about the gamma ray sources. And this is something that visually one can see very nicely if you compare the IGRET sky. IGRET was the previous instrument before Fermi-LAT. It had around 270 sources, most of them unidentified. And this is the sky after the 2 years of operation of Fermi. So you see that the number of sources increased by basically 1 order of magnitude, and many more sources could be identified. And then this is the third catalog, 3,000 sources. Now we have the fourth catalog, 5,000, and now there's a new catalog with more than 7,000 sources coming online. And I think it's important to stress that the number of sources increase faster than the square root of time. So this is not limited by background. And the reason for that is that many of these sources are variable. You can see that there's many AGNs. And then sometimes these sources are not flaring. You observe, you don't detect, and then the next day the source flares, and then you can detect it. So it's beyond the sensitivity. The detection of new sources go beyond the sensitivity of the instrument. Anyhow, you can see that there's huge improvement in the number of sources, classes of sources, and the quality with which the sources can be studied, and so on. And similar things happen in the TV sky. So this is the situation 20 years ago, basically at the onset of the new generation of Cherenkov telescopes. As soon as the current generation started to operate, 10 years later, we increased the number of sources by an order of magnitude. And now the situation is that we have more than 300 sources. So again, you see huge improvement in the number of sources, and then also the number of classes of gamma ray sources that we know about. Okay, so now we shift a little bit, and I'll tell you a bit about the MAGIC telescope. This is one of these instruments for gamma ray astronomy. Consists of 2 Cherenkov telescopes of 17-meter diameter mirror dish. So you have here a nice photo of the telescopes, and this is the control house where we have the trigger, the DAQ, and this is the place from where the shifters operate these telescopes every day. And the telescope operates from tens of GeV to actually 100 TeV and beyond. So the collaboration consists of around 300 physicists from 13 different countries. Most of the countries are European, but we also have some contribution from India, Brazil, and actually quite some contributions from Japan. And yeah, last year was actually a very important year for us because we turned 20. So MAGIC started to operate, MAGIC first telescope started to operate in October 2003. So we turned 20 years last year. And we also reached this milestone of 200 publications in peer-reviewed journals. So that was last year. And then this year, we already made 11 additional publications. So now our line is at 211 scientific publications. And these publications span over many different scientific topics, from conventional astrophysics, like gamma ray bursts, active galaxy nuclei, pulsars, and so on, and also fundamental physics studies like Lorentz invariance violation and dark matter searches. So as I mentioned last year, we were turning 20, so we actually organized a symposium that happened in La Palma, in the Hotel Taboriente at sea level. But yeah, and then we have like 150 participants, about 100 people from the MAGIC collaboration, and 50 external scientists, very distinguished external scientists, as you can see here from these names. So it was actually a very nice event for everybody, for magicians and for people outside the collaboration. And one of the events also had to do with a tour of the visitor center in the Roque Los Muchachos. This is actually nice, very nice place, and they were very nice with us. They actually gave us a room where we could actually have a dedicated exhibition for magic that lasted for 3 months, and then a fraction of this exhibition moved to a permanent place in the visitor center. So now we are part of the history of the Roque and explained here in this in the visitor center. Okay, so one of the reasons that magic has been quite competitive over the last 20 years, despite operating for 20 years, is that the instrument has been changing over time. And this is something that is described very nicely in this plot. This is the sensitivity, integral sensitivity, versus the minimum energy of the analysis. So basically, this is the minimum flux that you can detect at the level of 5 sigma in 50 hours of observation. I think the battery is, let's see. Yes, it works. So basically, lowering this plot is better. It means that you can detect a lower gamma ray flux. And this sensitivity we have in 2005. This in 2008, but we upgraded the DAQ system. This is the sensitivity we had in 2010 when we had the second telescope. And this is sensitivity after the upgrade that happened in 2012. And so you can see that the sensitivity improved basically by a factor of 4 here in the sweet spot around 300, 400 GeV. But even more important is the improvement in sensitivity below 200 GeV. Here you can see the sensitivity improved by about 1 order of magnitude. And since the sensitivity here is limited by background, a factor of 10 improvement in sensitivity is a factor of 100 in observation time. And that means that what we could do with 100 hours of observation below 200 GeV at the very beginning of the mission, and now we can only do in only one hour of observation. So that's, of course, is a huge discovery potential, and that's one of the reasons that magic has been quite competitive over the last years. We have been improving over time. And more recently, so what I show you here was improvements over the first 10 years. And more recently, we had some additional improvements where we actually developed a special sum trigger system, which increased the energy threshold from 40 GeV to 20 GeV. And we developed strategies to observe a large zenith angle. When we observe a large zenith angle, there's a larger pool of light on the ground. So we increase our effective areas by a big factor at the expense of only functioning at the highest energies, and also having less good signal background separation because everything is further away. Anyhow, these are not standard observations. We don't operate regularly with these strategies. They are a bit more complicated to analyze. There are some complications, but these are strategies that we can use when we need it. For instance, we need to observe a pulsar that has an energy cutoff, a few tens of GeV, then it's beneficial to observe with this sum trigger system. Or if we want to study some sources at multi-TeV energies, then it's also beneficial to use this strategy to improve the effective area and therefore reduce the amount of time that we need to accumulate a number of photons. Yeah. Okay, so magic has been operated for 20 years, so there's been many interesting results over the last 2 decades, and some of these results had a big impact in the community. And actually, the first publication that had a big impact in the community is it's about the detection of LSI 61303. At the moment of publication, we thought it was the first microquasar at very high energy gamma rays. Later on, we actually learned that it was not a microquasar. There was a lot of discussion before we submitted the paper, but at the end, we were convinced at the moment of submission that it was a microquasar. Later on, we learned it was a binary system. So it was not the first microquasar, but actually the second binary system after Hess had detected LS 5039. Still is a very nice publication. It's heavily cited. I think it has more than 400 citations. And this source has been observed with magic actually multiple times. I think we have 5 or 6 papers on this source. We also detected for the first time variability with time scales as short as 2 minutes. That was the first time that something like this happened. That was for 501. We detected for the first time a flat spectrum of the quasar at very high energy gamma rays. For the first time, we detected pulsed emission from a source at very high energy gamma rays. That was the crab. First time that we detected fast variability in a FSRQ, fast variability in a radio galaxy. First time that we detected gravitational lens laser at very high energy gamma rays. First time that we detected TV emission in a pulsar. The first time that we make an association between a high energy neutrino and a very high energy gamma ray source. And we also detected for the first time a GRB at TV energies. Yeah. So yeah, you can see that MAGIC was actually designed to explore, to detect new things. And here you can see that this is something that we have been doing over the last years. And now I tell you a little bit about GRBs. Many of you know them very well. Maybe others don't know that well. These are the most powerful transient objects in the sky. And there are two kinds, if you classify them observationally. We have short GRBs, which are associated with binary neutron star mergers. And then we have the long GRBs that are associated with collapse of dying massive stars. And then in the emission, there are two phases. There's the prompt emission that happens mostly at MeV and lasts few hundreds of seconds at most. And then we have the afterglow that is broader in energy from radio to gamma rays, and actually it can last. Now we know it can last for days. So here I have an example. This is the energy flux versus time in log scale. And here you can see the prompt emission, and this is the afterglow emission for two different GRBs. You can see that these are very distinct emissions. So basically, the current understanding is that the prompt emission happens where we have shells that collide with each other in the jet that is produced when the massive star collapses. And then the afterglow is produced when the jet is collides with the ambient medium, and then it decelerates and opens up. So Doppler factors decrease, and then you get this decrease of the broadband emissions. That's our current understanding. And before 2019, that was the picture. We knew about almost 200 GRBs that were emitting at GeV energies, detected with a LAT, but we didn't have any single gamma ray burst detected at TV energies with Cherenkov telescopes, even though we were looking for these beasts for 30 years. And the main reason for this problem is that there's two big observational challenges. One is that these GRBs are very short. They last from seconds to minutes typically, and they happen at random locations of the sky. So you need to point quickly your telescope if you want to catch them. And the other one is that many of these GRBs are very distant. And then what happens is that these very, very high energy gamma rays, in their way towards us, they interact with the photons from the EBL, and they produce electron positrons. So basically they disappear. So the amount of gamma rays that we detect from a very distant source decreases by factors of, could be by many orders of magnitude. And that also makes it very difficult to detect gamma ray bursts at very high energy. But yeah, in 2019, finally, we actually detect the first GRB. This is the announcement that we made. This is an astronomer telegram that was issued only a few hours after the GRB took place. So at that moment, we claim a detection at the level of 20 sigma. In the final analysis, it was more than 50 sigma. And here you see the first TV spectrum from a GRB. This is the spectrum that we measure. This is energy flux versus energy, and this is the spectrum that we measure with the MAGIC telescopes. And this is the spectrum after correction for the EBL. So here you can see that the TV, the absorption is by a factor of 300. So this is the observed spectrum has an index of 5.4. The intrinsic spectrum has an index of 2.2. So it's a huge difference. Even though this GRB was relatively nearby, 0.4. So typically GRBs happen at redshifts larger than 1. And what I show you here is the energy of all the photons that we were detecting versus time. And what you can see is that these energies are actually higher than the synchrotron Barnov limit, which means that these photons that MAGIC detected cannot be synchrotron emission. And that means that there should be a different component responsible for the gamma rays that MAGIC was detecting. And what I show you here is a broadband SED for this GRB for 2 different time intervals. And this is modeled with with a scenario that has synchrotron emission and inverse Compton emission. It's a one-zone synchrotron self-Compton scenario. And we show that this theoretical scenario can describe nicely the broadband SED and the evolution of the broadband SED. So for the first time, we claim a different component in a GRB in an unambiguous manner. And that has a number of implications, but one clear implication is that the energy content of the GRB is basically twice the one that we thought initially, among many other things. So that has big implications. That was published in Nature in 2019. So after MAGIC reported the first GRB, actually, a few months later, Hess reported the second GRB in May 2019, and in August 2019, the third GRB. And then a year later, MAGIC reported the fourth ERB. So it was interesting. We were looking for GRBs for 30 years. We saw nothing. And then suddenly, after seeing the first one, then 4 came basically clustered in time. And 2 years later, then LASSO detected this the brightest GRB of all times, which is orders of magnitude higher, more bright than these guys here. Unfortunately for us, this happened during the day and during moon. So it was the worst possible moment for us, while for LASSO was happening basically at zenith. So it was the best possible way for them to detect this. So nature is like this. Theoreticians say that this is an event that happens once every 10,000 years. So I guess we will not catch the next one. Anyhow, so yes, as I said, there were, with MAGIC, we have 2 GRBs, this one, and this is our second GRB, and actually this year we published the data from the second GRB, which happens to be at redshift 1.1, which is the most distant very high energy gamma ray source to date. And so yeah, this published this year. This is the detection at the level of 6 sigma. And here you can see the spectrum. Observed spectrum, intrinsic spectrum, quick change in the power law index. And here you can also see that the spectrum starts at 40 GeV. And here you can see very clearly the importance of having sensitivity below 100 GeV. Otherwise, we would not have detected this GeV. For instance, our competitors, Hess or Veritas, they don't have this level of sensitivity to detect a GeV like this one, because above 100, 150 GeV, there's basically no signal. So yeah, that shows one of the big strengths of the MAGIC telescopes, that we can actually detect things below 100 GeV, which allows us to see things that are very far away. And we also show in this paper that the broadband SED of this GeV is also consistent with this one-zone synchrotron self-Compton scenario. So basically, as up to now, all these GeVs can more or less be explained with this scenario, synchrotron self-Compton. Now we only have 4 or 5 GeVs, so we will see whether this hypothesis survives the test of time. I'm sure in the next years we will detect more GeVs with LASSO, with MAGIC, with LST. So yeah, we will learn more about GeVs. But it is a really interesting reports over the last years. And here, just also to mention very briefly that we also have a hint of a signal at the level of 3 sigma for a short GeV. And in this case, this gamma ray emission is not consistent with the one-zone synchrotron self-Compton scenario. But anyhow, these are 3 sigma signals, so who knows? I mean, this could be a statistical fluctuation. We will see. Of course, the interesting thing of short GeVs is that they have far fewer than long GeVs. So it's actually nicer to detect those ones. And also they are expected to produce gravitational waves. So in fact, the only source that has been detected with gravitational waves and with photons so far is this neutron-neutron star merger that was detected with Fermi, integral, and advanced LIGO. So short GeVs are very interesting. So far, no short GeV detected at EV energies, but at least we have a 3 sigma hint. Okay, so now we change topics, and I report about the explosions of novae. In this particular case, is the detection of a recurrent nova symbiotic binary system, Fuji. In this case, this detection was announced for the first time by the Hess collaboration. That was announced in this astronomer telegram on August 10th. The optical trigger happened in August 8th. And in August 9th, Fermi reported that there was gamma ray emission from this object. Both Hess and MAGIC started to observe in August 9th. Unfortunately, our observations were a bit shorter, and our signal on the first night was not reaching the 5 sigma level. So we didn't issue an ATL. So in this case, Hess was actually faster than us. But then once you know that there are gamma rays, TV gamma rays coming from this object, the next question is how these gamma rays are being produced. And here I must say that MAGIC was actually faster in putting down what is the physical interpretation of the data. So both collaborations basically posted the paper on the archive more or less at the same time with 1 day difference. Alicia knows very well. She's one of the corresponding authors of this paper. And yes, okay, there's a long story here, which I'm not going to get into. But the important thing is that, okay, both collaborations agree in the interpretation, which is that these gamma rays are being produced by high energy protons. And here you have a visual kind of visual confirmation of that. This is the same data, Fermi data, MAGIC data, same data, modeled with 2 different scenarios, one with high energy protons and the other one with high energy electrons. So the agreement with the high energy protons is better and also is more natural. In the case of the electrons, we need an additional break, which needs to be put ad hoc. So yeah, so protons are accelerated in nova, at least in this nova. Okay, we need to detect additional nova to confirm whether this happens in a regular basis. And then we also learned that if all the novae are like this one, then the contributions of novae to cosmic rays is important only in the vicinity of the novae, within a few parsecs. So farther away, then the contribution from novae to the production of cosmic rays is only a tiny fraction of all the cosmic rays that are produced in supernova remnants. And the next explosion that we expect is T Corona Borealis. This is another symbiotic nova. In this case, in principle, it happens every 80 years. But optical astronomers have claimed that the explosion should happen in the year 2024. Actually, the period was from April to October 2024. That was the period that we were given. And we were very excited about it because this nova is actually 3 times closer than Ares of Fuji. And since the emission is isotropic, then in principle, we expect 1 order of magnitude more photons than for Ares of Fuji, the previous nova. And of course, there's a once in a lifetime opportunity to study in situ particle acceleration in a cosmic ray object or cosmic ray accelerator. So there's a lot of excitement in the community, from radio to very high energy gamma rays. We were all preparing for this explosion. There was also a lot of popular videos, like this one, for instance, from Neil deGrasse Tyson, more than 3 million visits in 2 months. So it's a really, really nice event. Unfortunately, it has not happened so far. And now I hope it doesn't happen until January or February, because now the visibility is very, very bad for us. We would only observe a very large zenith angle, which is not the best conditions to observe this kind of object. But here, for instance, you can see an estimate of what we would see with the MAGIC telescope. This is Ares of Fuji. This is the flux versus time. This is Ares of Fuji, and different colors is the significance with which we would detect this object in an observation of 5 hours. And you can see that every day we would detect the source at the level of 50, 40 sigma, and we would detect this emission. Okay, there are different extrapolations depending on how things go, but basically over month time scales. So this is really, really an amazing event. And if in addition to MAGIC, we add LST1, I'll tell you a little bit about combination of MAGIC and LST later on. But the fact is that we can have joint observations of MAGIC and LST. Then we improve our significance, our sensitivity, so we can detect with higher significance, we can detect it for longer times. Yeah, so this is as far as gamma ray observations is concerned. We also can observe this nova with this intercity interferometry strategy. Actually, Juan is one of the experts, and actually several people here in IAC are also working on that. So the idea is, if through this strategy, the idea is we convert our gamma ray telescope into an optical telescope that has an amazingly good angular resolution, fractions of a millisecond. And then the idea is that if we point to this object during the first hours, we should be able to see how the expanding shell, the photosphere, is actually moving. And that would be, of course, very important to better understand the object for the theoretical interpretation later on. So that would be fantastic. And this is only with magic. Again, we can actually combine magic and LST1, which improves further the sensitivity of these observations. So this is a fantastic event, and we were all prepared to observe. Unfortunately, it didn't happen. Now I hope it doesn't happen until January, February next year, so that we can catch it. Okay, so now we change topic again, and now I move to active galactic nuclei, and in particular the jets of active galactic nuclei. These are the most powerful particle accelerators, persistent particle accelerators. So GRBs are the most powerful transient particle accelerators. These are persistent particle accelerators. And AGN jets are also the largest structures in the universe. You can reach even megaparsec scales. The jets are produced, and actually we know that they also accelerate particles up to at least 100 TeV in the case of electrons. And some people claim that they are also partially responsible for the ultra-high energy cosmic rays. And since jets are produced in the vicinity of supermassive black holes, then they also are direct probes of black hole physics. So they are really, really fascinating objects that have been studied for many decades by the astronomical community. Unfortunately, the knowledge that we have on AGN is still quite superficial. There's many open questions, like the jet composition, the magnetic field in the jet, how strong it is, what is the structure, how particles are actually accelerated, is in shocks, turbulence, magnetic reconnection, and what produces the variability that we see that can go from years down to timescales as short as minutes. So these are really fundamental questions, and we actually don't have answers to these questions. And so actually, one of the reasons why it's so difficult to study AGNs is because there are three big observational challenges. First of all, is that these guys emit a very wide energy range from radio to very high energy gamma ray. So you need to cover 18 orders of magnitude in energy in order to study properly these objects. The emission is variable, and the variability goes from tens of years down to minutes. So you need to cover different time scales over 6 orders of magnitude. And then they're also especially extended. The jets are especially extended from milliparsecs to megaparsecs. So you need to cover angular sizes of 10 to the 9. And in order to complicate things further, the variability and the spatial extension are energy dependent. And also our ability to measure those things are energy dependent. So you see, it's really a very complicated task. And that's actually one of the reasons why even after 50 years, the knowledge that we have on these guys is still quite limited. So sometimes when I'm studying AGNs for a while, and sometimes I feel like in this hitchhiker guide to the galaxy, where people are waiting for millions of years for the ultimate answer to life, the universe, and everything. And at some point you get 42, and then what do I do with this 42? But nevertheless, if we tune a little bit the questions, maybe this 42 is not that bad. Maybe instead of 42, we could have 4 to 1. and then so maybe we are going in the right path towards the understanding of AGNs. The ultimate answer to the jet magnetic field, particle acceleration, variability. Maybe is my 41, my Carrier 41. Anyhow, so the study of AGNs with a number of instruments that cover from radio to very high energy gamma ray, even multi-messenger, even other messengers like high energy neutrinos, in a way somewhat similar to what happens in our collider experiments here on Earth. We have very different experiments. You accelerate particles, you make them smashed, and then you try to learn about what physics is happening there. So similar things happen in a distant AGN. Of course, a big disadvantage is that we don't have knobs that we can use to choose which particles get accelerated up to which energy, what is the target material. We just simply get what nature gives us. And this, of course, is a big disadvantage. The big advantage is that they allow us to study extreme processes that cannot be reproduced here on Earth. So that's an advantage. Potentially, we can see some things that we will not be able to see here in our in our collider experiments. And of course, they are much cheaper because at least the accelerator we don't need to build. We only need to build the detectors. But yeah, because we don't control nature, we just simply get what nature gives us. We need to keep observing over many years in order to integrate over sufficient data effects. And that basically leads to this, that you need to have long-term multi-instrument observations of these objects if you want to really understand them. And obviously, if these multi-instrument campaigns happen on bright AGNs that can be detected in short time, then it's very efficient because you don't need to invest a huge amount of resources to basically characterize the whole broadband SED. And you can study how the broadband SED evolves with time. And that offers you the possibility to see things that might be more difficult to see with other objects that are less bright, simply because you need to integrate over longer time scales, and maybe you actually miss viability because you simply are not sensitive to that. And obviously in this game, it's very important to combine the data with data from novel instrumentation that provides a perspective that was not available before. And this is something that happened very recently with the XP satellite that allows us to detect polarization in the X-ray emission for the first time in AGNs. So XP was launched in December 2021 and has been operating since then, providing for the first time information about the polarization in this band. So the first XP observations of Macayan 421 together with MAGIC happened in May and June 2022. And then we actually learned that the polarization in X-rays is much larger than the polarization in optical and radio. And in this time, even though the variability was not very high, we could see that there was correlated variability between X-rays and gamma rays. And that means that the X-rays and gamma rays come from the same place. So basically, we put the two things together, and that tells us that, that this is consistent with a picture where we have a stratified jet, where we have a region where we have high energy particles producing X-rays and gamma rays. And then we have a more extended region with the lower energy particles with a less order magnetic field that produces optical and infrared emission. Yeah. And so that was these observations May, June. This was already published actually this year and last year. And in December 2023, we actually had another campaign together with XP, and we observed for the first time a very strong flaring activity in gamma rays with fluxes beyond twice the flux of the Crab Nebula, which is 4 times the typical flux of Macayan 421. And we also have a lot of variability in X-rays, in X-ray flux, but also in the polarization and the electric vector polarization angle. So you can see that the electric vector polarization angle is more or less aligned with the polarization angle in optical. This red is optical, and purple is actually here radio. So it's more or less aligned, but there are some fluctuations. And then the polarization degree is also, varying much more than optical and radio. That is more or less flat. So this is the first time that we could see this, and this is actually a paper that has just been submitted for publication in ANA. So it's very, very fresh results. Let me actually go here. So yeah, so this is the ratio between the polarization degree in X-ray versus polarization degree in optical. So 1 would be same as optical. Less than 1 is less polarization that optical. So in the case of radio, we have less polarization, optical, and then X-ray we have more, and it's playing all the time. And here, just on this day, we actually have a very dedicated observation with XMM, very long observation. So we could see actually the whole evolution in the X-ray emission around this time. And this is something that you can see here. This is the X-ray emission with the XMM. And this is the hardness ratio versus time. And this is the hardness ratio versus flux. And here we actually can see that there's a counter clockwise loop. And if we go back to the classical papers from Kirk and Mastikiadis, 98, they say that these kind of loops happen when the acceleration timescales are comparable with the cooling timescales that need to happen close to the maximum electron energies. So basically what it's telling us is that the X-rays and the gamma rays are happening at the moment where you have the highest energy particles. And yes, so that's also important information. So the fact that the X-ray polarization angle is parallel to the jet axis suggests that we actually have shocks that are compressing the magnetic field in the jet. The fact that the polarization in the X-ray is larger than optical, that is larger than radio, implies that we have a stratified region. So from higher order magnetic field to less order magnetic field. And then the fact that we have a variability in the X-ray, and there's a lot of scatter in this relation between variability in the X-ray polarization and X-ray gamma ray connection. That implies that there's a lot of turbulence. So it's not a smooth acceleration. So there's a lot of turbulence, as predicted by this simulation. So this turbulent plasma crossing a conical shock. So this is very, very interesting observations that is telling us what is happening in the jet of this AGN. So we decided to model this broadband emission with a simple scenario where we have two very simplistic scenario where we have two regions, a compact region where produce the gamma rays and X-rays embedded into another region that is responsible for radio, optical, and Fermi. And the size of these two regions is constrained by the polarization measurements. And by doing that, we actually could model for every single day, we could model the broadband SCD. So here we have the extended region. Here we have the compact region, and this is the interaction of this extended and compact region. And with this model, we could actually describe very nicely the data. Basically, with the variability given by changes in the magnetic field and the injection of electrons, with the magnetic field being stronger in the compact region, so closer to the shock, and no correlation between the flux and the parameters, which support the stochastic nature of the variations. So that's actually a very interesting study that has just been submitted for publication in ANA. Yes, and I would like to stress the fact that gamma rays are actually playing a fundamental role in this time domain in multi-messenger astronomy. So what I show you here is the three most recent multi-messenger sources. This binary neutron star merger that was detected with gravitational waves and gamma rays. Then we have this connection between a high energy neutrino source and a gamma ray source, TXS 0506. And then we have this, the most significant neutrino source in the IceCube catalog, NGC 1068. And here actually the important thing is that we don't see gamma rays. This is something that you can see very nicely. Here, this is the neutrino spectrum from IceCube. And these are the upper limits with magic after 130 hours of observation. These upper limits are 2 orders of magnitude below the neutrino flux. And since neutrinos are expected to be produced with gamma rays, the fact that we don't see gamma rays by more than 1 order of magnitude, almost 2 orders of magnitude, means that these gamma rays need to be absorbed in the region where the neutrinos are being produced. So that brings us very important information about this object. So you see that gamma rays play an important role in the 3 multi-messenger sources, and actually magic is playing already an important role. 2 out of the 3 contain magic data. Okay, so now very quickly I change topic again, and now we move to the dark side of the universe. You all know that most of the matter content of the universe is not visible, it's dark. And this is clearly one of the biggest mysteries that the scientific community needs to address. Now, the big problem is that dark matter mass range is huge. It extends over 90 orders of magnitude. So the constraints here are actually limited by the de Broglie wavelength that would be actually larger than the galaxy. And here the constraints are given by the fact that if that would be the case, it would be too compact. And then we would have a more clustering of the matter with respect to what we see. But over these 90 orders of magnitude, it could be anywhere. So we don't know what is dark matter. And then, of course, many scientists worship this religion of the WIMP miracle, meaning that if the dark matter particles are TeV in mass scale with a cross-section that is the weak interaction, then they will produce a dark matter abundance that we see. That would be also a very nice story. We all will love it. But so far, we actually don't have any single experimental evidence that this is the case. Now, if this is the case, of course, then this is the most interesting region. And if this is the case, then Cherenkov telescopes like MAGIC and now LST are fantastic instruments to observe in here. And in fact, most of the searches that MAGIC has performed are actually here. Although we also look for ultralight dark matter particles and also heavy dark matter particles. So very quickly, just to mention that there are three ways of trying to look for dark matter. Either you produce it in collider experiments, you detect it in underground experiments, or you detect in an indirect way. And then basically indirect detection consists of seeing what happens when there's a decay or annihilation of dark matter particles. They produce some other particles that decay and then produce the messengers that we detect. And if the messengers are neutral, then they point directly to the dark matter source. And we know what are the locations in the universe where there's dark matter because we can see the gravitational effect. So that, of course, is a very interesting thing because we have neutrino telescopes and we have gamma ray telescopes. So we are actually looking for dark matter in this way. And I think it's important to stress that dark matter searches in an indirect way are actually crucial to understand the dark matter problem. All the three are important. Of course, we should do all the three searches, but indirect searches are really very relevant because even if we produce something in the lab, we actually don't know if it is dark matter until we relate what we have produced with, locations in the sky where we know that there's dark matter. So indirect searches are fundamental. And they also allows us to search some phase space that are more difficult to detect here in the lab in terms of annihilation cross sections, decay times, and so on. So yeah, very quickly for our Cherenkov telescopes, we have two prime candidates, galactic center and dwarf galaxies. They have advantages and disadvantages. The galactic center is the place where we expect the strongest signal, but we also have the strongest backgrounds. So it's a difficult target. But of course, if we have annihilation into two gammas, then it would stand out because it's more difficult to produce with conventional astrophysics sources. And this is something that we did last year. We published a search with more than 200 hours on the galactic center. We didn't see, unfortunately, any hint of a signal. So we use these non-detections to put constraints into the velocity average cross section. Yes, so we did it for two different dark matter profiles. We actually don't know precisely what is the dark matter profile in the galactic center, close to the galactic center. So we published the results for two different dark matter profiles. And the important thing is that at TeV energies, our results are compatible with HESS. Above 20 TeV, our results are actually slightly better than the constraints with HESS. And the next step, the most competitive search of dark matter with dwarf spheroidals, actually is going to be a publication which involves a large number of instruments: Fermi, Hawk, Veritas, HESS, and MAGIC. So dark matter should be the same everywhere we look and should be detected with all the instruments in a similar fashion. So we just combine all this data. We have a combined likelihood analysis. I need to go very quickly because I'm a bit delayed. But basically, with this combined search, we have the most constraining limits with dwarf spheroidal data. And here you can see this is the thermal relic cross section, which is already excluded at least a few hundred GeV for some annihilation channels. Here you have the plots for different annihilation channels. This is a paper that will be submitted soon for publication. And then we also look, as I mentioned, we search for dark matter, very light dark matter particles. In this case, this is a study where we actually look at potential distortions in the gamma ray spectrum of a source with a high magnetic field, like the Perseus cluster. And if we don't see these distortions, then we can put constraints in this phase space here of the coupling constant versus the mass of the action. Okay, so very quickly, now look into the future. Of course, the LST-1 is already up and running and producing very interesting results. One of the most interesting ones is the detection of OP303. It's a laser at redshift 1. And this can be done because of the high sensitivity of LST at the lowest energies. So it's already up and running. And since LST is actually close to the two MAGIC telescopes, we actually last year we started to put them together and to have stereo analysis with the three telescopes. And this is something that we published last year, and we showed that the sensitivity improves by a factor of 1.3, 1.5, which implies a reduction in the observing time by a factor of 2. And this, of course, opens new opportunities to detect faint sources. And because of that, next year we are going to perform a coordinated MAGIC LST-1 observation that will be evaluated by the same TAC. So it will be with a coordinated scientific program with the two collaborations. And here you can see the construction of the LST array. LST array is 4 telescopes. This is June. And now here you have August, where the arch and the camera support structure was being put in LST-4. This is LST-1, LST-4, LST-3, and LST-2. And And this is basically the situation last week when I was there at the rocket. You see LST1, 4, 3, and 2. And the construction is really going super, super fast. We hope it will be operational in 2026. And this is really, really an impressive welcome message for everybody that goes to the rocket. You arrive with the car, and then you see these huge telescopes telling you, yeah, here we are. So it's really, really impressive. It's going to be impressive when everything is completed. Okay, so with MAGIC, we are also starting to expand our physics portfolio with interesting interferometry observations. So very quickly, we take a pixel from one telescope, a pixel with another telescope. We see how strong is the correlation between these two signals for different baselines. And then this is telling us about the angular size of the object that we are observing. So we are using here the telescope, not as a gamma ray telescope, but as an optical telescope. And Cherenkov telescopes are great for that because of the large collective mirror and fast time resolution. So yeah, so this year we actually published our first performance paper for this way of operating. And here you can see the measured diameter of stars, known stars versus the reference size. You can see there's a nice agreement that shows that we actually can measure the size of stars down to a fraction of a milliarд second. So this is what is already published. And the next step is to expand this to the LST1 and the other LSTs. And for that, we are using a ERC grant by Tarek and the group from TMAT. And we are now moving into this direction already with LST1 and later on the 4 LSTs. And this is important because we don't only get additional photons, but we also get additional baselines. So we can see the size, measure the size of the object on different directions. And that's also very important. So right now we have this angular resolution, a fraction of a milliard second, which is basically an order of magnitude worse than the resolution of the Event Horizon telescope in radio. And so in the future, we expect not to only measure diameter of stars, but maybe also the shape of the stars, so fast rotators, binary systems, or nova explosions. As I mentioned, if we observe quick, we might be able to see how the nova expands. So we are actually quite excited about this. So yeah, so MAGIC has been operated for 21 years, 211 papers already out. In the next years, besides regular gamma ray observations, we will perform joint observations with LST1 and intensive interferometry. The LST commissioning is finishing for the first telescope. The other telescopes are being built very quickly. 2026, the telescope should be operational, and then they will start the commissioning of these telescopes. So there's going to be lots of gamma ray results. And very quickly, maybe 1 or 2 more minutes, just to mention that there's a gigantic boost in the instrumentation to observe extreme environments with gamma rays, with the current generation of instruments and the new generation that is now coming online. All these instruments provide a perspective that it was not available a few years ago. And of course, this has a huge implications. I mean, history shows us that whenever we observe astronomical objects, extreme environments that cannot be reproduced on Earth with new instrumentation, interesting things can be learned. Happen with the gravitational laws of Newton, atomic structure that comes from spectroscopic observations of white dwarfs, indirect detection of gravitational waves that come from observations of a binary pulsar system in radio. Now, more recently, the discovery of neutrino oscillations that come from observations of the sun with neutrino telescopes, the direct detection of gravitational waves, observations of black hole mergers, and also more recently, the detection of a supermassive black hole here on the center of our galaxy with optical interferometry. So basically, what you can see is that in all these big breakthroughs, you have observation of extreme environments, things that are not reproducible here on Earth-based laboratories, with new instrumentation, radio telescopes in the second half of the last century, neutrino telescopes since the end of the last century, optical interferometry and gravitational waves, yes, basically the last few years. So the recipe is basically the observation of extreme environments with powerful instrumentation. And this is already happening in many different areas. Now the question is where the next breakthrough is gonna happen. It's gonna be high energy neutrinos, ultra high energy cosmic rays, high energy gamma rays, maybe gravitational waves again, or interferometry. So in any case, well, we don't know, but I have high hopes that it will happen in gamma ray astronomy, in particular, gamma ray astronomy with combination of neutrinos, cosmic rays, and gravitational waves. And I think I stop here. Thanks for attention.
Thank you very much, David, for the very comprehensive talk. Do we have questions or comments?
Thank you very much for the talk, also making it possible to understand gamma rays when you work in a field where you still work with nanometers and angstroms. You mentioned in the beginning that the duty cycle for like telescopes like MAGIC, etc., is comparatively low. And is this due to the fact that those telescopes are technically optical telescopes? Because I mean, I guess the gamma rays are not influenced by some clouds, but the Cherenkov radiation at the end is. Is this the reason behind that?
Yes.
It's
So yeah, basically yes. So like optical telescopes, we only operate in good weather atmospheric conditions during dark nights. Maybe optical telescopes can operate during full moon. We cannot. For us, it's very difficult. We are also affected by clouds in a different way. So basically, what happens is that some of the light that is produced in the shower gets absorbed. So then the amount of light that we collect with the telescopes is less than the amount of light we should detect. Now we have learned how to partially correct for that. We have a LiDAR system. It's a laser that shoots up, and then we see the backscatter light. And then by the time information of this backscatter light, we know where the clouds are, how thick they are, and where they are. And we have some strategy to correct our data for that. So up to some extent, we can correct for clouds. But if there's too many clouds, then
at which height is it, or in which layer is the other Cherenkov radiation produced?
Yeah, that depends on the incoming or the energy of the incoming gamma ray. So typically it's around 10 kilometers above us. Yeah, but very low energy gamma rays a bit up. Low energy, high energy gamma rays can go down.
Any more questions or comments? Okay, I have a very, if you had to bet in which area you will make a discovery with gamma rays, which will be your bet?
In which area will make a discovery?
Something groundbreaking, breakthrough.
Yes, so it's completely educated guess, but one possibility, of course, is the detection of a very distant source at TeV energies. If the source is at redshift 1 or 2, and we detect TeV energies, TeV photons, this is incompatible with what we understand about the propagation of gamma rays towards us. And one possibility is that the gamma rays travel in the form of a different particle, like could be actions. And the form of actions, they don't get absorbed. And then they get converted into gamma rays when they get into our galaxy, in the magnetic field of our own galaxy. So we detect gamma rays that we should not be able to detect. So that could be actually a very nice thing.
So dark matter, dark sectors, sort of.
That would be one. Yeah, of course. Okay. Yeah. That would go to bring us to Sweden.
Okay.
To collect some medals.
You got the right answer. Isn't it a bit surprising that LASSO has detected no more GRBs?
Well, so LASSO is an extended shower array. So they detect the tail of the particles in the shower. So the energy threshold is very high. So typically it's the order of 1 TeV. Now this boat was, something very exceptional. There are so many photons that even with a very low sensitivity, they could actually detect photons at a few hundred GeV. But typically it's not the case. You see, all the GRBs that we have detected with MAGIC and HESS, we would not have detected them if our sensitivity would be only above 1 TeV. So it's actually, in my opinion, it's not surprising. I think I doubt that they will be able to detect many GRBs. Yeah. In fact, even with bright sources like Macayan 421 or 541, I was collaborating with Hawk. Okay, Hawk sensitivity is not as good as LASSO, but even there were very big flares that we could see very nicely on our time scales. And they basically, you compare different days and they are basically compatible with days where the source was not playing. So these detectors have very low sensitivity.
But they can see the prompt emission.
You see, the interesting thing is that the boat which was huge in number of photons, the detection that lasts or so is actually not the prompt. It's actually the afterglow. So at the very beginning, they actually see nothing, and after some time, they see emission going up. So particles, they start seeing the gamma ray emission produced by the afterglow, and then they decreases. So this is a bit scary because prompt emission would be fantastic to detect with gamma rays. And in fact, with all this variability, that would be fantastic for Lorentz invariance violation, for instance, but you have, changes by factors of a few in seconds. But the fact that the both was not detected in prompt, it's a bit scary. Maybe the prompt emission is simply not producing very high energy gamma rays. Yeah. But it's one event, so I mean, we will see. But yeah.
Okay, if there are no more questions, let's thank David again for his beautiful talk. And
you.
have a nice lunch.
Thanks. Bye-bye.